Hi, I'm Mira.
And I'm Jeremy.
And for our Machine Learning 2 project, we decided to build an English to French translation model. So we were motivated by this because in an increasingly interconnected and globally minded world, communication is a very critical aspect that translation models can help to fulfill communication gaps between peoples. So we aimed to build our own translation model for this, going between English and French, and used OpenNMT's Python framework in order to successfully build a model. And we also decided to explore how results would compare in between two optimizers, Atom and Adigrad. So for a closer look into the data that we used here, any sort of translation model is going to be built off of a parallel corpus, which just means that it's a set containing a sentence in both the source and target language with a one-to-one in between the sentence and its translation. So for this, we used an open source public data set, which consisted of translated documents from the United Nations. In order to train, it had around 76,000 lines. And as you can see here with this example, one line is in English, and then that line is also in French in the other text file. For a little background on the model itself, the OpenNMT is a neural machine translation model that was developed in 2016, and it's very robust nowadays. It supports many processing and translating procedures, many of which we used here that we'll touch on in terms of feature engineering and the model itself. The version that we used is based on PyTorch, and it is ultimately a sequence-to-sequence transformer model in order to actually complete the translation task.
So there are several steps we have to take in order to feature engineer the data into vectors that can be used for training. The first thing we did was we filtered the data, and like we said before, the OpenNMT package comes with built-in functions that allow us to filter the words. And by doing so, we were able to remove misalignments, empty segments, and duplicate lines. Next, we had to tokenize the data, and this included splitting the sentences into smaller units of meaning that can be used to learn and identify relationships between the tokens. And we used a package called SentencePiece, which was a unsupervised text tokenizer that used byte encoding to help us with the subwording and tokenization tasks. And subwording was something else we did. And subwording is to replace tokens that are similar enough to an existing vocab word with that vocab word. And this allows us to reduce the size of the vocabulary and save on space and memory. And it removes the amount of unknowns in the data, which makes the learning more accurate. This is the configuration for the OpenNMT neural network that we used for the trials. We had a preset vocab size of 50,000 words. We had train steps for our stochastic gradient descent of 3,000 steps. So it would take 3,000 steps maximum before we stop the updating of the weights for stochastic gradient descent. And we had batch size of 4,096 tokens. And we had a model architecture of 6 encoding and decoding layers, 8 heads, and a hidden size of 512, as well as a dropout rate of 0.1 between both of these trials. And the two trials that we looked at were, again, Atom versus Adigrad. So a brief explanation between the differences of Atom and Adigrad. These are both adaptive learning optimizers to penalize the learning rate for over excessively updating the weights. And you can see above that that is the weight updating algorithm that is typically used in machine learning and neural networks. So Atom, the mathematical background of it is that it combines momentum and RMS props V, which are two other adaptive learning optimizer algorithms. But Atom does the job of combining these two into one that reaches the optimal weights even faster by increasing the learning rate for weights that haven't been updated as much and decreasing them for weights that have. And this prevents weights from being excessively updated and prevents bias. ADGRAD does a similar thing, and but uses a slightly different mathematical background to its formula, but it also reduces the learning rate for greater iterations of updating of a particular weight. And the results, the model was able to translate between English and French. It was pretty good at doing so, and we can take a look at the English file and the reference file. So above, we have the translated sentence from French to English using the OpenNMT model. And then below, we have the reference, which is the actual sentence. So that was the predicted is on top, and the testing one is on bottom.
And then in terms of evaluation for our model, we use the bilingual evaluation understudy, or BLEU, which is the industry standard in being able to assess accuracy of translation models. And it does so by taking the translation and the reference file and measuring the similarity of the two based on the n-gram overlap between the files and assigning a score between the range of 0 and 1, with 1 being a perfect match between the source and target. And we found with this that the Atom Optimizer performed better, producing an accuracy score of 68.4%, which was significantly better than the 48.7 for the ADGRAD. And what this can be interpreted as is that the Atom Optimizer is computationally more efficient and is able to update the weights for a better and faster learning rate, which we can see then in terms of the fact that the time for the training on the Atom took less time compared to the ADGRAD, as well as having that higher accuracy score. And this was more or less in line with our expectations from research we had done beforehand. Some takeaways that we had from this project as a whole is that translation models need a really robust data set to train a model to completion, and many professional translation systems that actually have like user feedback have more layered machine learning in terms of their data set is growing, and new training is being incorporating on top of new data and new words that users are translating from, whereas ours was more static in terms of we gave it the data and that was all of the data it had to train. And so kind of continuing on that, we could see that the pre-processing for our project in particular was really crucial, as was the NLP techniques that we used, as it's really important to get the data to a form where learning can be done in the most efficient manner possible, and really lessen that computation time. As well as large-scale learning models in general are really time-consuming to train. The ADGRAD for us took about an hour and a half, but we had a pretty limited and standard size vocabulary. So imagine something that is, 2, 3, 5, 10 times larger than what we were using. And because of that, you can see the accuracy would also be fine-tuned pretty slowly, but the more you're able to incorporate new data and new learning, the better that accuracy is going to be. And then looking to the future with this project, some things that we could improve on and potentially add if we had more time would be improving accuracy by looking at other evaluation metrics as well. So there's the translation error rate, the BERT score, and COMET, which are other industry accuracy predictors that exist for translation models. We could also explore more of OpenNMT's configurations, as you can configure your model in a number of different ways. And there are a lot of potential things that we could tweak with to improve our accuracy. And lastly, potentially being able to expand our model to include other languages and even fictional languages, although this is really dependent on being able to get the data into a form that will work with the model. Thanks for watching.
Thank you for watching.